hopefully you did as well on your test as students in here did on theirs. They did a fantastic job, as I expected. Chapter 8, a fairly straightforward chapter. As we get into chapter 9, we want to go kind of change gears here. We're not going to completely ditch the trig we've learned. Okay, trig isn't going away yet. We're going to take one last vestige of trigonometry here in chapter 9. As we move into chapter 10, moving forward, that's where we're going to kind of depart from the trigonometry. We're going to switch to that other half of the class. But for now, we're going to make one last application of trig, but it's going to feel more like algebra. In fact, everything I teach today is something you should have learned in Algebra 2. So it should be fairly straightforward for you. I want to go back and review imaginary numbers. So in your notes, let's let that be the heading of the next section, imaginary numbers. And as I believe I mentioned in Algebra 2, imaginary numbers kind of get a misnomer here, like they don't exist. Like imaginary friends. If you have imaginary friends, okay, that means you have no friends. Sorry, okay? Well, imaginary numbers, it doesn't mean you don't have a number, but for a long time it was thought that they could not exist. Well, obviously later developments prove they must exist, and they've got application to different science concepts, alternating current, Ohm's law being one of them. But imaginary numbers, just have that name imaginary, and the name kind of stuck, so the name is still there. Basically, we know the square root of 9 would be technically two values, both positive and negative 3, right? Whereas the square root of negative 9 we said equals nothing. There's nothing that you could square to get a negative 9. And so that was just said that you cannot take the square root of a negative. It's impossible. But again, as mathematicians and scientists were confronted with the need to take the square roots of negatives, they said, well, let's conflate a value. The most basic square root of negative of all would have to be the square root of a negative 1. Can't get more basic than that. That is the most basic negative for which you could take a square root. If you do negative 0, you would, but 0 ain't negative, okay? And they said, well, let's represent the value with the letter I to represent the imaginary concept that had already been constructed previously. If the square root of negative 1 is I, and I would like you to put that in your notes with a star next to it, square root of negative 1 is I, then we could take something like the square root of negative 9 and say, well, that's the square root of 9 times negative 1. Or, as you know from algebra, the square root of 9 times the square root of negative 1, which would be the positive negative 3 times the I, or positive negative 3i. And so we have the ability then with the square roots of negatives, by representing the square root of a negative 1 as I, just kind of separate the negative from the rest of the value and then take the square root, and it's kind of as if we stick an I on the end. The way that I like to say it is, you see the square root of a negative, pull out your I, then you take the square root of the 9 to get, of course, the positive and negative 3. So write this down in your notes, something from your algebra class. If you see the square root of a negative, first, and underline the word first, pull out your I. See the square root of a negative, pull out your I first. So that if I had the square root of negative 36, you can't take the square root of a negative. We got to do what? Pull out your I. Now, it's a 36. What's the square root of 36?
6.
Technically positive and negative 6. Normally, though, you'll recall if the square root is already printed there for you, there's the assumed positive, so we'll assume the positive here as well. If you take the square root, for instance, x squared equals 36, you're taking the square root, now you would say positive negative 6. So had this been a negative 36, positive negative 6i. If we just had the square root of negative 7, how would I write that, Jamie? Pull out your
I
times the square root of 7. What's the square root of 7?
is square root of 7.
The square root of 7. So we're going to leave it just like that. I squared root of 7. We pull out the I, that's all we could do. Here we pull out the I and we can take the square root. If we had something like the square root of negative 32. Again, first we gotta. So we get I square root of 32, and I can't take the square root of 32 like you can 36. But I can do more with the square root of 32 than the square root of 7, because I can at least reduce the radical, remember?
Square root of 16 times 2.
Good, factor that into 16 times 2, where I'll take the square root of the 16.
5 times 32.
Good, remember, your numerical coefficient always at the front, the radical always at the back, which means your I would have to come in the middle if you had both. Always before a radical, but always after the numerical coefficient. Do we see how to lay out a square of a negative when we pull out the I? Questions on that? Vaguely remember learning that in Algebra 2? All right. Well, let's take a look then at the next thing in your notes as we discuss imaginary numbers, powers of I. Powers of I. Well, there are four fundamental powers of I. First of all, I to the first. Can't get any easier than that. I to the first is just I, because anything in the first is itself. You knew that one already. Feels like a waste writing it down, doesn't it? All right, I squared, though. Let's think about this. I is the square root of negative 1. And so if I square I'm squaring the square root of negative 1. And when you square a square root, you get the radicand. So if I square the square root of negative 1, I must just get negative 1. Put a star next to that. That's perhaps one of the most important powers of I, is the I squared, and remembering that it really is just negative 1. Well, I cubed would simply be I squared times I, right? So that would be a negative 1 times I, which is negative I, or negative 1I, but I'm too lazy to write the 1. And then if we had an I to the fourth, well, that would be I squared squared, or I squared times itself, right? Well, negative 1 times itself, or negative 1 squared, is just 1. And these are the four fundamental powers of I. I say fundamental because this is what they all come back to. Everything comes back to this. So if you had a bigger power of I, for instance, let's suppose we had something like I to the 8th. Well, any power of I can be broken into one of these at its simplest form. I to the 8th, for instance, would be I to the 4th times I to the 4th. Well, what's I to the 4th? Times I to the 4th, which is equals 1. Even if you said, well, what about I to the 5th? Well, that's I to the 4th times I. I to the 4th is 1 times I is. Because I to the 4th is 1, it's the last power we need to memorize. Because everything can come back to 4s. You could even take out, for instance, you got like I to the 15th. You could even think in terms of this. You could say, well, this is I to the 4th, I to the 4th, I to the 4th, I cubed. You could do that, but mathematicians are lazy. So what I do instead is I say, well, every 4 is another 1, right? So how many 4s are in 15? 3. Or another way to say, what's the biggest multiple of 4 that is in 15? 12. Right? It's 3 of those 4s. Well, let's just do another 1, 1, 1. So basically every multiple of 4 i's is another 1. So my word is basically say, well, this is I to the 12th times I cubed. Because this is a 4, a multiple of 4, it's 1. Just ignore it. I really get an I cubed. And I cubed is? So that means that I to the 15th is negative I. Let's take this approach for something bigger. For instance, I to the 26th. Well, what's the biggest 4 in 26? 24. Take 24 out of 26. How many i's you got left?
2.
I squared. What's I squared? Negative 1. So all bigger powers come back to that. I to the 20th. Well, wait a second. That is a 4. Well, that means it must be what? 1. Because the 4th powers are 1. It's 5 of those 1s, but it's out of the 4th, 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 right? That's 1, 1, 1, 1, 1. All multiplied still gives 1. So if it is a multiple of 4, you know you get 1. If it's not a multiple of 4, pull out the multiple of 4. Whatever it leaves you with, you have its value from this list. What if I had an I to the 13th then? What would that equal? Take out 12 i's, because that's a multiple of 4, leaves you with a single I, which is I. What if I gave you, I to the negative 17th? Let's review. We haven't seen this in a while. What does a negative exponent mean? Reciprocal. So remember, this means 1 over I to the 17th, right? Well, okay, big deal. So we do 1 over whatever we got. What's the biggest 4 in 17? 16. Take it out. How many i's are left? Just 1. So 1 over I. We're done. So what if I had I to the negative 14th? What's the biggest 4 in 14? 12. And if I take out 12 of those, it leaves me with an I to the negative second, or 1 over I squared. But what is I squared? So what is 1 over negative 1? And negative 1. And there's my answer. Does that make sense? I practiced with a few of these in your textbook. Page 180, do 1 through 6. Page 180, numbers 1 through 6. Is this something, by the way, that we remember from Algebra 2? Okay, good. And it's Friday here. If you're watching, I'm not sure what day it is for you, obviously, but here it's Friday. Brains are tired. We're ready for the weekend, so I'm glad we're not breaking anyone's brain here. All right, let's see how we did. Number 1, with I to the 10th, what does that become, Jamie?
Negative 1.
It becomes I squared, which becomes negative 1. What about I to the 12th? Quentin?
1.
It is a 4, so it's just 1. What about I to the negative second, Jamie?
Negative 1.
1 over I squared, so 1 over negative 1, but that's just negative 1. Number 4, Quentin?
1.
1 again, because it is a 4. Didn't mean to steal that one and put it on the board. I to the negative 9th, Jamie?
1 over I.
Good, it becomes 1 over I to the 9th, which is, pull out your 8 i's, leaves you with just a single I. So 1 over I, there you go. Number 6, here we're multiplying I to the 6th times I to the 8th. And when we multiply like bases, class, we add the exponents. I've got 6 i's times 8 more i's. That's how many i's total being multiplied here? 14, of which, if we have 14 i's, pull out 12 of them to leave me with 2 i's, and I squared is negative 1. The other way you could do it is you could say, well, pull 4 out of the 6, that leaves me with an I squared. And I to the 8th, I mean, that is a 1. I squared times 1 is I squared, that's negative 1. So you could do it that way as well. Either method would work. Questions on the 1 through 6. But the way I did it initially gave me a chance to review that when you multiply like bases, you add the exponents. Good review there. Numbers 7 through 12, of course, the first few, 7, 8, and 9, we see just some basic roots where we have the square root of a negative, got to pull out the I. But I want you to consider something like this. What if we had the square root of a negative 3 times the square root of a negative 8? Again, anytime we see the square root of a negative, class, first thing we got to do, pull out your I. So that this becomes, Jamie,
wait a minute. I times the square root of 3.
and this would become, Quentin,
2I times the square root of 2.
good, I times the square root of 8, or we could reduce it to 2I squared 2. Then we're going to multiply. And remember, when you multiply radicals, you multiply the coefficients together, class,
2.
and you multiply the radicals. But notice we created an I squared. I squared is negative 1. So this is 2 times negative 1 times the square root of 6. Now this is why the first thing you've got to do is pull out your I. Because if you don't, you're just like, oh, well, negative 3 times negative 8 is positive 24. Let's factor that down. Let's say that's 4 and 6. That gives me 2 times the square root of 6. You lost the negative because you didn't pull the i's out first. So i's have got to come out first. This would be wrong. Always pull out your i's first. Or if I had something like this, the square root of negative 16 plus the square root of negative 49. Well, of course, you can't add the numbers like that, right? You can't add radicals unless they're similar, but the first thing we'd want to do anyway is pull out your I. And once we've pulled out the I, we take the square root of 16 to get, what'd you call me? My gangster name. And then the square root of negative 49 gives us, class, 7i. So our answer is 11i. There we go. All right, questions on that? We're going to do 7 through 12 now. 7 through 12. electri anytime you see the square root of a negative. All right, number 7, what did you get? Here we go again, Jamie.
4i.
4i. Number 8, what did you get, Quentin? 5i. Number 9, Jamie?
2i times the square root of 3.
The 2i times the square root of 3. Number 10, Quentin?
3ix.
Good. We're going to take out the I, of course. We're going to take the square root of the 9 to get 3, and we're going to take the square root of the x squared to get x. Notice we use alphabetical order here. So I, although it has this actual value, it's not so much a variable as a constant, it still looks like a variable, so we're going to still put it alphabetical order. Does that make sense? All right. Okay, I was about to say, did I steal? No, I didn't do that exact one. Number 11, Jamie?
7i.
7i. And then number 12, again, the first thing we got to do, class, is pull out the I to get the 3i squared to 27x to the 4th. The 27 we're going to factor into, pull out the 3 from the 9 to get a 9i. We'll leave the 3, and then the square root of x to the 4th is. So here we kind of see the same thing, the alphabetical order, but also the radical still at the end, numerical coefficient in front, and the letters in between in order. Questions on 7 through 12? We good to go on those? All right. Now, again, I kind of showed this a moment ago. One of the applications of imaginary numbers is it opens up a world of equations that we could not solve before we knew them. For instance, if I gave you this equation, you're going to write it down in your notes. X squared plus 12 equals 0. The original way I taught you to solve quadratics when you were in 9th grade was to factor, set the factors to 0, and solve, right? We even did a little of that in our trig equations earlier last semester. But you can't factor this. It's not factorable. But I taught you that with an incomplete quadratic, we could isolate the x squared and then take the square root. Well, again, if you don't know what to do with the square of a negative, you just say there's no solution. And as far as real numbers are concerned, there is no solution. But you do get imaginary roots here. What do you end up with when you take the square roots of negative 12, JB?
Yeah. Positive, negative. Let me see. 4. Choose times the, or I times the square root.
There we go. We're taking the square root, so we got to put the positive, negative. We're going to pull out the I. We're going to factor 4 and 3, where the 4 comes out as a 2, the square root, and we're going to leave the 3. And we get our imaginary answers here. Okay? Write this one down if you would. X to the 4th, negative 45, is equal to 35. Something else that we saw in Algebra 2, but we did not see it often, was the presence of a 4th root. Now, when we did see it, we usually saw complete quadratic form as opposed to a pure quartic like this. And so we would solve this very similarly to how we'd solve a quadratic, an incomplete quadratic. We're going to isolate the x to the 4th by adding the 45 class to get 80. Did I copy that right? I guess so. We end up with an x to the 4th equals 80. And then we've got to take not the 4th root, because we don't know how. We're going to take what are called successive square roots, you might remember. So we'll take the square root of x to the 4th, and we'll take the square roots of 80.
2 times square root of 10? No.
16, 5.
Ah, if we went 16 and 5, we get a little bit better values here.
4 times square root of 5.
Positive negative 4 square root of 5. But that's x squared. Then we take the square root again, so we end up with all 4 answers. Remember, a quadratic should have 2, a quartic should have 4. So we take the square roots again. Square root of x squared, x. And here I'm going to separate this out. I'm going to say the square root of 4 square root of 5 and the square root of negative 4 square root of 5. Obviously, the square root of 4 class,
2.
but we take the square root, so
So
positive negative 2. And when I take the square root of a square root, whenever you take the root of a root, you multiply the indices to get the 4th root of 5. We saw that in geometry toward the end of last year one time. I think we saw it in Algebra 1 and Algebra 2 just briefly, but wanted to show it again. And then here, we got to take the square roots of negative 4 squared of 5. And as soon as you hear the phrase square root of negative, pull out the I. Of course, the square roots of 4, and then the square root of the square root of 5 gives us the, and here we wind up with 4 answers. 2 of them are real irrational answers. 2 of them are imaginary answers. Technically irrational, but we don't really say irrational. That's a category of real numbers. We get our 4 answers still. Questions on that with the successive square roots. And then we also ran into this little problem. If I had something like x squared negative 2x positive 5, we said this is called a complete quadratic equation. A complete quadratic equation. And for complete quadratics, we said, well, these are ones you do want to go ahead and backwards FOIL and set the factors to 0. The problem is, it doesn't factor, does it? You can't split the 5 up to get a 2. We say when you can't factor, you can either use the quadratic formula or you can complete the square. And we're going to use completing the square a lot later on in the year, so I want to use this as an opportunity to review this with you. Remember, when you complete the square, the idea is that we've got the start of a perfect square trinomial. We just don't have the right number here to be a perfect square trinomial. So we're going to keep the beginning of the equation, but we're going to ditch the 5 class as a negative. Then we're going to fill in the blank with what would complete the square. And remember, there were 2 steps which we're going to memorize really well later on this semester to complete the square. You take half of the b, that's the coefficient of x, and square it. So we take half of 2 and square it, we get 1. But you got to add it to both sides, right? You can't just randomly put a +1 over here. What you do to one side. So here we end up with a PST, and over here we end up with essentially negative 4. This here is a perfect square trinomial. I completed the perfect square trinomial. I completed the square, with the intent that a perfect square trinomial can easily factor into a binomial squared. Over here, I had x squared equals negative 12. And since it was an x squared, I took the square root. Well, here I have an x negative 1 squared equaling a negative 4. And since it's squared, I can take the square root of both sides. Been a little while since we did this. Coming back to us? When you take the square root of x negative 1 squared, we get, and when you take the square roots of negative 4, you get positive negative 2i. But the x isn't by itself yet. We have to add the 1 to both sides. But is 1, a real number, a like term to positive or negative 2i imaginary numbers? No, so you can't mix the 2. So we're going to leave our answer as 1 plus or minus 2i. And our answer here is not real, though part of it's real. It's not imaginary, though part of it's imaginary. We call this a complex number. Do you remember talking about those? We're going to look at those in just a moment. Questions on completing the square first. Vaguely remember doing this at some point in your life? All right, I want you to practice a few of these, or a couple of these. I want you to do 14 and 18 now. They're on page 180. I want you to do 14 and 18. They're on page 180. miss the good old days, Jonathan. Life was simpler then. No college decisions.
Nap time.
Nap time.
Snack time.
Snack time. Oh man. I'm not sure if you on YouTube can hear. She's reading nursery rhymes to the 3-year-olds on the other side of the wall. Check your work. Incomplete quadratic. Isolate the x squared, take the square root, but when you take the square root, you're taking the square root of a negative, pull out your I. Factor 4 and 2 to pull out a 2, and leave the other 2, and then positive, negative. Good to go on the first one. On the next one, my initial thought would be it's complete, set it equal to 0, but then I realized, wait, there's no way you're going to factor that. So put the 9 back where it was, keep the 2x here. Same quadratic as it turns out, right? It has a 2, so half is 1, squared is 1. What if it had been a 4 right here? Half and square, so you would get a 4 that you'd add to both sides. What if it was a 10? 25 on both sides. What if it was a 18? 81. What if it was a 5 right here? You cry, exactly. Just kidding. Half of 5 is 5 halves. You do a 25 fourths. You would avoid the decimal at all costs. Fortunately, it was an even number. We like even numbers. You might remember we talked about completing the square. We really would like even numbers right there. Odd numbers, quadratic formula time. But it was even, so put the 1. That gave us a negative 8. Well, that looks familiar. With the x negative 1 squared, take the square root of x negative 1 squared. Of course, that's x negative 1. We already know the square root of negative 8 is that positive negative 2y squared of 2. The 1 moves over as a positive 1, but again, it can't combine with this imaginary stuff, so we just leave the 1. And again, we get a complex value there. Questions on those? Good to go on both? All right, then let's talk about complex numbers. We've got about a little less than 15 minutes left. Let's go ahead and do a quick crash course review on complex numbers. First of all, you know what the definition of a complex number. Complex number is part real, part imaginary. A complex number is part real, part imaginary. That means it is a binomial. And it's going to be in the form, the real, which will represent as A, plus bi, which will represent the imaginary. So this binomial form is called the standard form. Now, if you peek ahead, which I'm not encouraging you to do necessarily, if you were to peek ahead, you'd see there's a trigonometric form as well of complex numbers. Obviously, that's not something we talked about in Algebra 2 because you didn't know trigonometry yet. Okay, we're going to obviously get into that here this year. But the standard form, you might remember the A plus BI. You put the real first, then you put the imaginary, where A represents any value, and B represents any value that's within I, which makes it imaginary. Make sense? So, for instance, if I had the imaginary number 5 plus 3i, well, obviously the real part, class, is the, and the imaginary part is the 3i. If I had a 2 negative I, obviously the real part is the, and the imaginary part is the negative I. Not just an I, but a negative I, right? Well, what if I wanted to add my complex numbers? Kind of a sub-point here. What do we do to add complex numbers? Well, you might remember these are binomials, and when you add polynomials or binomials together, you combine like terms only. Well, reals are like terms, imaginaries are like terms. So you combine them. What would I get to add these complex numbers together? 7 positive 2i. So just add the real, add the imaginary. If you want to get that in your notes, you can. At the same time, it is kind of stupid easy. So no hard feelings. You're like, I think I got this without writing it down. All right, what if I had Let's go with an 8 negative 5i added to a 7 negative 3i. What would that give us for our answer, Jamie?
15, negative. Oh, no,
Here I have a 15 because 8 plus 7 is 15. What is negative 5i, negative 3i?
Negative 8i.
Negative 8i. There we go. What if I had a, running out of board space here, so I'll go down here. What if I had a 2x negative 7i plus a negative 4x positive I? Quentin?
Negative 2x, negative 6i.
Negative 2x, negative 6i. Easy enough for add the real, add the imaginary. All right, next subpoint. Subtracting complex numbers. Well, I actually taught you back in 9th grade Algebra 1 what to do here. Do we ever really subtract? Yeah, the inverse. This might be the last time you get to write this in your notes. Add the inverse. So pretty much, too lazy to make up new ones. If it said all these same things we just added, it says minus. I said no, that's not what we do. We add the inverse. And what do we get, Jamie?
Now we get 3 plus 4i.
What about here? We add the inverse. What do we get, Quentin?
1 minus 2i.
Says subtract, class. Nope. And what do we get, Jamie?
6x minus 8i.
6x minus 8i. Easy enough? Questions on that? Next thing in your notes, multiply. Complex numbers. Well, realize these are binomials, right? And in fact, they will almost always be similar binomials. How do we multiply similar binomials, class? FOIL. So there's your notes. FOIL. So, first, outer, inner.
1i.
Positive 1i. Negative 5, positive 6 gives you a positive 1i. Last,
Negative 3i squared.
negative 3i squared. However, one little important note is to remember that I squared equals negative 1, because when you FOIL, you will get I squares. And since I squared is negative 1, this is 10 plus 1i minus 3 times negative 1. Or in other words, that just becomes a positive 3. Well, notice this plain old 10 and this plain old real 3, they can combine, they're both real.
15.
And then my lonely positive 1i just stays lonely. Questions on that? All right, what about the next one? What do we get when we do our initial FOIL here, Jamie?
56. Negative 59. Then positive 15 I squared.
Good job with the signs there. Negative times negative does give you that positive. Good job with the outer inner. Negative 24, negative 35 is the negative 59i. Right here, though, I squared is really what?
Negative 1.
Times positive 15 is really negative 15. Well, there's real 56. There's real negative 15.
41.
And of course, we will also keep the
Negative 59i.
and there's my complex answer. Question on that? All right, so what if we had the one I erased a minute ago, 2x negative 7i, and suppose we multiply that by the negative 4x positive I. Quentin?
Negative 8x squared. 30i.
Good, a positive 30ix. Good job keeping the letters alphabetical.
And negative 7
But I squared is
-1.
times negative 7 is really
7 positive.
and there's my answer. Now technically we would want to put real before imaginary. The 7 is real, as is the negative 8x squared. So I'll put the 7 negative 8x squared. That way we don't have a leading negative, though that's not absolutely critical in the case of imaginary numbers. There's my real plus, and there's the imaginary. Some texts may want you to group the real as one collective. So we have real plus imaginary, but I'm not too picky about that. Questions on that? All right, add, subtract, multiply. You're smart. What comes next? Divide. Keep in mind what I is. Class, what is I? Sorry? Well, it represents the word imaginary because that's its origin, but what does it represent? What does I literally mean? The square root of -1. That's what I is, remember. Well, that means that what I have here is a 2 minus the square root of -1. Are you ever allowed to have radicals in the denominator? You're not allowed to have i's either. So if you can't have an I in the denominator, this is how we show division, right? Fraction bar, we have to get the I out. And you'll recognize since it's complex, that means we have two terms, real, imaginary. And for a two-term radical denominator, we multiply by the conjugate, remember? So if this were like the square root of 3, we'd multiply by 2 plus square root of 3. Well, it's the square root of -1. So we multiply by 2 plus the square root of -1, where we multiply rather by a 2 plus I. So put that in your notes. Multiply by the conjugate. Of course, what we do to the bottom. And so in the denominator, my chalk just ran out, so go with that one. In the denominator, since we multiply by the conjugate, we've artificially created that sum and difference, remember. So 3 steps. That's if you square a binomial. To multiply a sum and difference or a pair of conjugates, remember, square the first, square the last, put a minus sign between them. There we go. Again, if you had to multiply and double, you're still going to have an I. And that's the significance of the conjugate, is to square the first, square the last, put a minus sign between them. Because that I squared can become a -1. And so 4 minus -1 gives me, notice, no more radical denominator. It comes out completely real. Numerator, we're going to have to obviously FOIL here then. And when I FOIL, what do I get, Jamie?
10 plus 11 plus 3i squared.
Of course, we know I squared is really -1, so 3 times -1,
Is -3.
-3. But that can combine with the 10 to just get 7 plus 11i all over 5. Again, some texts will want you to separate this and say there's your real, 7/5, and there's the imaginary. So you can see the a plus bi. I'm actually okay with this answer or that answer. I'm cool with whatever. I'm lazy, so I typically leave it as the top form. But again, depending on the teacher you might have in college, they may want the other form, wanted to share that with you. All right, so let's suppose we had 8 minus 5i, and we're dividing it by the 7 negative 3i. What do I need to do to divide these complex numbers? Quentin? Multiply by the conjugate. What is the conjugate, Jamie?
7 plus 2i.
And what do I do to the bottom, Quentin? All right, so we're going to multiply by the 7 plus 3i in the bottom. We're going to multiply by the 7 plus 3i in the top. In the denominator, Jamie, what do I have to do? 3 steps.
Square the first, square the last, put minus sign between.
Always, 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 right? So we square the first.
49.
We square the last.
9i squared.
Good, and we put a,
Minus sign.
but we know I squared is.
-1.
So if we have a -9 times -1, it really becomes a
9.
+9. So we end up with a denominator of
58.
58. In the numerator, Quentin, what do I gotta do?
Square for, or foil.
Foil, and when I foil, what do I get?
56. Negative 11. Negative 15 squared.
But
I squared is negative 1. So plus 15. That's 71 plus, or 71 minus 11.
all 1158, or 71/58 minus 11/58 I. Questions on this? Do you vaguely remember learning all of this in Algebra 2? Again, nothing that I taught you today was new, but a really good refresher, hopefully, for you on complex numbers. You're going to practice with imaginary and complex numbers over the weekend. For homework, page 180. Page 180, I want you to do numbers 13 to 29, the odd. Page 180, numbers 13 to 29, the odd. We'll take a look at all of this next time. We'll go over a couple of new things using complex and imaginary numbers as well in our next lesson. Have a wonderful rest of your day, and when the bell rings, you'll be dismissed.